we have a 1 MeV neutron that strikes our target. And our target is indium-115. I told you that it had 4 successive elastic scatters. Of 165 degrees, and 220 degrees, and 83 degrees, and then finally 308 degrees. And I asked you, what is the final direction of travel? And remember, when our neutron is coming in, for the first scatter, if it goes for 165 degrees, if this is 90, then it's going to be coming back in this direction. You overlay the grid again. And then you show a 220 degree scatter, overlay the grid again, overlay the grid again, or realizing that this is the beauty of center of the mass system, we know the final direction of travel is just a summation of all the scatters. So in this case, it's 165 degrees plus 220 degrees plus 83 degrees plus 308 degrees. And that total
Professor, the
yes.
the second degree, it's 222, not 220.
Okay. That would change my answer, so hang on a second. Okay. So I had that come out to be 778 degrees. That is true, but that's not normally an angle you'd work with because we're looking for something between 0 and 360. So you can take 360 away from that. That's still greater than 360, so you take 360 again. So my final answer would have been .58 degrees. So compared to the initial travel coming in, after it undergoes all 4 elastic scatters, this is my final direction, where that angle is 58 degrees. If I then go back and I ask you, what is the final energy? We know that the equation is KE out divided by KE in is equal to A squared plus 2A cosine of theta plus 1 divided by A plus 1 squared. That's for one scatter. If you find this value coming out after one scatter, substitute it back in for the incoming energy, change the angle, you'll have a new out, substitute that back in, get a new one, substitute it back in again, and after the 4 scatters, you'll have what the final energy out is. If I summarize all this, And then I'm going to use each and for each one of these, I'm going to put in a squared plus 2a cosine of theta plus 1 divided by a plus 1 squared. And in each case, my A value is equal to 115. And then I'm going to substitute back in the angle for each of those. So in this particular case, the first angle of scatter was 165. This one was 222. This one was 83. And the final one was 308. Of course, my incoming energy was 1 MeV. So the value I got was 1 MeV, and I had this reduced to 0.966. Had this one reduced to 0.970. Third one reduced to 0.985. And then the final one reduced to 0.990. When I multiplied all of those out, I had my final energy out as 0.917 MeV. And I could have kept doing this depending upon if I had 5 scatters, 6 scatters, whatever. You can still use this chain rule to get a final answer. Any questions on what we did for either the direction of travel or the final energy? Then the next thing I asked you for, what was alpha for indium? We know that that is A minus 1 quantity squared over A plus 1 quantity squared. And what is alpha? It looks at the energy remaining after one perfect backscatter. So if we went back to our equation, and we substitute in here 180 degrees because that would be a perfect backscatter, this reduces to this. And so for our indium, this would be 115 minus 1 squared over 115 plus 1 squared. And I had that value come out to be 0.9658. This is the energy remaining after one perfect backscatter. So if you look at indium, the max energy lost in one perfect backscatter is 3.42%. Because I'm just taking this and making it into a percentage. So indium would not be a particularly good moderator. Any questions on that?
Yes, I have a quick question on this. So
Sure.
is the value of alpha the 0.9658 or the 3.42%?
Alpha is this value.
Okay.
This is energy remaining after one perfect backscatter. And the way this is written, this is going to be a percentage. So 96.58% of the energy of any neutron coming in, it's energy independent, will remain after one perfect backscatter. Okay. Then the next thing I ask you is, on the average, how many scatters would it take to take our one MeV neutron and thermalize it? So we know that that equation is N is equal to the natural log of the energy in divided by the energy out divided by squiggle. If A is equal to or greater than 6, then we know that squiggle is equal to 2 over A plus 2/3. Indium, our A value was 115, so we can surpass that, so we can use this. So squiggle is 2 over 115.667. When you do that math, I had that come out to be 0.017291. If you substitute this back into here, the energy in was 1 MeV. But 1 eV is 1 EVs. Energy out is thermal, which is 0.0253 EV. Remember, these have to cancel the unitless to take the natural log of that. When you did the math on that, I had this come out to be 1011.65 collisions. But we know whenever we have a fraction, we always round up. So the answer was 1012 collisions. You don't always have to use this equation just to take an energy to thermal value. I could have asked you, how many collisions does it take on average to reduce a 1 MeV neutron to a 100 keV? If you did that, we're reducing this to 100 keV. We have to make sure we have like units there. Then you could use this to find the average number of elastic scatters for indium to do that. So you can do it between any energy range, and that's valid. Any questions on that? And then the extra credit, I don't know if anybody tried to do that yet. For scatter, we have a center of mass system. And remember, in that case, your reference point is the compound nucleus. So everything occurs around that. So for the center of mass system, if this is your compound nucleus, when the scatter occurs, the beauty of this system is if the target goes off in that direction, you know the scattered neutron must go in that direction. because linear momentum must be conserved. Linear momentum is 0. So, and remember, momentum is defined as mass times velocity. So this mass times its velocity is a vector going in that direction. The neutron mass times its velocity is a vector going in that direction. This vector must exactly equal that vector to have that cancel out. So we also know that this is isotropic, which means the scatter has an equal probability of going in any direction. So when you look at the cosine average value of theta for the center of mass system, this is 0 because it is isotropic. If you're sitting here, it has a probability of going in any direction. So it's 0. If instead, though, we made this scatter in the laboratory system, we know that that angle is psi. And in this case, your reference is not the compound nucleus. You're sitting away from this and you're watching this. So again, the linear momentum on the right has to equal the linear momentum on the left, has to equal the linear momentum of the compound nucleus. So when you're looking at this, with the target being stationary, the neutron coming in with some velocity in that direction, then the compound nucleus, by this principle, must move slightly in that direction. So when you look at the target as to how it's scattered, the neutron and how it's scattered, this vector plus this vector must be a slight vector going in that direction, again, because of conservation of linear momentum. When they did the math on that, the average value of the cosine of value, the average value of the cosine of scattering in the laboratory system turned out to be 2 over 3a. In this particular case, our indium was 115. So that average value came out to be 5.8 times 10 to the minus 3. If we look to put that into an angle, that angle turned out to be 89.67 degrees. So with the neutron coming in this direction and then getting scattered, remember anything, if this is the initial direction of travel, anything that scatters in this direction is a forward scatter. And that shows what the forward scatter is for indium. And in reality, the scattering is isotropic, but because you're sitting there and this whole thing is moving slightly to the right, even though it's going uniform in all directions, for appearances to you, it does appear to be slightly skewed for forward scatter. And that's the answer that I was looking for. Any questions on that? Okay, I want to spend about 5, no more than 10 minutes on upcoming registration. They came out with a draft registration for the spring semester this morning. There are quite a few glitches with it because of mandatory COVID spacing rules. It's a mix again of LRON, online, and in-person, but not as many in-persons as everybody was hoping for, again, because of the spacing rule. It's being tweaked now, it's being adjusted again. Hopefully it's going to be out tomorrow. We've been guaranteed it will be out on Friday. I'm going to spend some time next week with you going through things, but I'd like to briefly go over things with you very quickly today for some upcoming dates. first Monday in November is registration for winter, if you need it, and the spring semester. On the Friday before, at the close of business, I'm going to collect every registration form that you submitted to me. I'll review it, sign it, date it. I hand walk it down to the registrar. And this is just like we've done in the past. I leave them with the registrar, and then the first thing Monday morning, the registrar's office registers everybody that submitted a written registration form to me. They then give them back to me that afternoon, and I will take them and put them in the box next to the security guard that you can pick them up at your leisure. But you can also go online into Banner and see what's going on. The registration coming back to me via the registration form in writing is mandatory for all the scholarship students, because I have to keep track of you to make sure you're going to graduate, keep tabs on the money I'm spending, that type of thing. I strongly encourage the others of you to still give me your paper registration forms, and I'll review them, turn them in, so that you can get registered automatically at 8 o'clock on Monday morning also. But it's not mandatory if you're not a scholarship student. The other thing I want to emphasize is I'm doing this as sort of a courtesy to you to get it in early, and they're going to register you. Now, you could still wait to register later. You could wait till the end of that week. You could wait till just before Thanksgiving, whatever you want to do. But just remember, the longer you wait, the greater the opportunity that other courses, labs, particularly for electives that you might want to take, they're going to be long gone. There are a lot of very popular electives that get snapped up within the first day or two. So if you dally, there's a chance that you might not get a course or a lab that you want for whatever reason. So I'd encourage you to do it up front. The other important dates coming up is by November 15th, I want everyone to register or apply for graduation. This is online at the college website. You fill it out. There is no cost to it. It'll go in. You will get a form back saying that you have registered for graduation, in this case in May. I will get the form back saying that you have applied. And then to complete that process, and I'd given this to you before, actually I've given it to you multiple times, but I also gave you at the start of the year. I have the plan of study, and I don't like the one that's on the website. It's sort of messy, it's busy. This is the plan of study for the nuclear program, and I need you to submit that by November 15th. You sign and date it, I'll review it, sign and date it, and then this will go into the registrar's office, and they will use this as your graduation audit tool. And then they typically do that graduation audit by the end of this calendar year, by the end of December. And then if there are any discrepancies, we resolve those so that you can still add classes, labs, whatever you need in the spring semester to graduate. Okay. I'm going to go over this more in detail as soon as the listing comes out. And just like I've done before, I will print out a copy of the spring schedule. I'll also print out a schedule of the winter schedule. I put one of each of these in the basket outside my office door. I also keep one inside with me so that we can discuss anything if you're on the phone or if you come by in person. But I'll go over that more with you. You might want to look at this form in the meantime. You basically, with the plan of study, you have to account for every course or lab. You must pass every course and lab in order to graduate, and you must have a cumulative GPA of 2.0 in order to graduate. But I'm going to go over this more on, well, probably Monday, or as soon as, if not Monday, it's going to have to be Wednesday, so that you can get all the paperwork to me by the end of next week. Any quick questions on that? Okay. I'm going to call out or send to you the exam momentarily. And just looking ahead, starting next week, okay, I'm going to start on chapter 9 for reactor theory, which is steady state reactor. The math and the physics are going to start to get significantly more difficult. I'm also going to start next week on pure bending in the nuclear materials science course. So I'm not going to give you any quizzes today due on Monday, but I would like you to read the first few pages of chapter 9. We're starting off with the multiplication factor, establishing the infinite multiplication factor, and then going on from there as to how you calculate that. And then if you have a chance in your text to look at pure bending, that would be gravy. I'm going to spend most of my time on Monday getting you going on this. My plan is right now on Monday, I'm going to have a review for Reactor Theory number 2 exam. And that exam will be on Wednesday of next week. It'll be in class. Okay. Again, start on this, do a little bit of review on Monday, whatever you'd like to review, and the exam will be in class on Wednesday. Okay. That being said, I'm going to go and now send you Okay, I'm going to send this momentarily. Again, I'm requiring that you sign at the end that you've either given or received help on this exam. Again, anything else, books, notes, papers, internet, anything else is fair game. So I've just sent that to you. Let me give you a minute to get that and look at it. Okay, I'm assuming you've got the exam now. So you're given the system below that has 3 applied torques as shown, and also 1 axial force as shown. As you read your way down, for each of the sections, and I've labeled them 1, 2, 3, and 4, I've given you physical information you might need, such as the length of each section, the radius of each cross-section. And then I'm telling you that sections 1 and 4 are exactly the same material. Sections 2 and 3 are also the same material. And then immediately below that, I have given you the properties of those sections. So section 1 and 3, the material there is exactly the same. And I've given you all the information you might need, plus I might have given you some extra information. Same thing for material 2 and 3, all the information you might need. It's a 100-point exam. So the first thing I've asked you is for a complete free body diagram of our system. Then I want to know, is each of our 4 sections safe? I want you to justify that. And then if you look at the very end, I have point M, and I've shown it in one view, and then I've shown it again if you rotate it 90 degrees. So I want to know, what is the final location of point M after you've applied these 3 torques and 1 axial force? That's the 100-point exam. Then for extra credit for 8 points, I'm telling you, release or take away the axial force. And then I want to know, if you apply a torque to the very end, I want to know what the value of that torque must be in order for M to return to its initial position. Any questions on the exam? Okay. I will be here for, I'll stay here for like 10 minutes, 15 minutes in case you have any questions. You can get back to me. After that, you can email me, but I'll be up in my office, or you can phone me. All the exams are due to be emailed back to me by 3:15. And again, don't forget that statement about giving or receiving help. If there's no final questions, this is not that difficult an exam. Just stop and think of what you're doing. You should be, I would think you could do this easily within an hour. Okay? Good luck.
Professor, I have one question.
Yes.
On the sketch on the exam, on the far right
Yes.
figure, 22,400 newtons, is that
Yep.
force coming like from the wall?
That is coming externally from right to left. It's an
Okay.
axial force going in the minus X direction.
Okay.
Any other questions? Okay. Good luck. I'll look for the exams today. Again, they'll be graded and back to you by Monday. And then I'll see you again in class on Monday. I will be around today to my usual 7 o'clock or so if you need to see me for anything. Again, good luck on the exam.